Hello everyone. We learned a little bit about graphs, and in this session we continue the introduction to graphs. Let's just start with some basic terminology of directed graphs. Here is the definition of adjacency for directed graphs. When u and v, so recall that in a directed graph we have vertices and we have edges which are directed. And the definition says all right, so if they recall that if the edges were directed, we show the edges by ordered pairs. So if this is E, and this is the rest of the graph, so E is the ordered pair of UV. And now this definition says that we call V to be adjacent from U and U be adjacent to V. And this is, okay, it's a terminology that it's not very commonly used, but it's very common to say that V is the endpoint or the end terminal and U is the beginning or the initial vertex. And when we have a loop, the endpoint and the endpoint or the initial point or the end terminal and initial vertex or the terminal or the initial vertex are the same. So here we have a vertex W and we have an edge. And note that a loop also can be directed in two different ways. And in any direction, its terminal and its initial vertex are the same. So therefore, here is terminal vertex. And this is initial, the beginning or the end. Now recall that in the case of an undirected graph, we had the notion of degree of V. The degree of V was the number of edges incident on V, where loops are counted twice. This is for the case of the undirected graphs. For the case of the directed graphs, every edge of a graph has a direction. So let's have V, and then there are edges that come into V, and there are edges that go outside of V, and then there is a notion of degree as before, as above, and there is also a notion of degree plus and a notion of degree minus. A degree minus is called in degree and is the number of edges that go into V, so that they go in. And the degree plus is called the out degree, and is the number of edges that go out of V. So if we want to use the terminology from previous slide, I should say degree plus of a vertex is the number of edges where V is initial vertex, and degree minus of V is the number of edges where V is the terminal vertex or the end vertex. So it's a very intuitive notion. Here is an example of a directed graph, and you see that it has loops also which are directed. And let's see for instance, the degree minus, and these are things that come into V, into a vertex of A is, in here is 1, and this loop is 1, therefore 2, and degree plus of A is things that go out. Let me write instead in degree. Let me write in degree and out degree, because it's already very confusing to use minus and plus. And there is a very nice formula, I mean, similar to what we had seen before. Let G be directed graph, then summation over all vertices, I recall that G is the ordered pair of V and that's V and E, and the summation over all the vertices of the in degree of V is equal to the summation over all vertices of the out degrees and this is exactly the total number of edge. That's because each directed edge, when you count the total in degrees, it contributes exactly 1 to the final terminal vertex. And when we are counting, for example, all the in degrees, and when we count all the out degrees, every edge like this one contributes 1 to just the vertex that it's its initial vertex. And right, so therefore counting the in degrees is the same thing as counting the edges, and counting the out degrees is the same thing again as counting all the edges. In this slide, we see some special classes of graphs which have special names. This one here is the complete graphs, as I also defined in the previous session. So a complete graph, K is denoted by K sub n, the complete graph over n vertices, and you recall that it was by definition where you have all the possible edges. So you have a set of n vertices and all the possible edges. And so K3, for instance, is a triangle, K4 is 4 vertex, K5 is 5 vertex with all edges, etc. And these graphs are called cycles. So clearly, so then every graph has degree 2, and undirected graphs. So Kn's are also undirected. So a cycle is a graph where so I should say I should also here say that it is a connected graph because it can be two separate pieces and you graph it. So, and anyway, it's also clear by the pictures here what we mean by a cycle. And these graphs here are called wheels. And so a wheel with n vertex consists of a cycle, and a central vertex is connected to all the vertices on the cycle. So these graphs for each n, so we have a wheel, and that's called Wn. Another interesting class of graphs are called hypercubes or n cubes. So a hypercube is when you take an n-dimensional cube and put a vertex at every tip of it. Well, to define it precisely, it can be defined in various ways, but here you should somehow try to see how it works by the actually the shape of it, and you see that the shape can be generalized. But to give a definition of an hypercube, it is the graph where you can, which its vertices consists of all the bit strings of length n. So I let me define Qn here. Qn is the set of vertices and edges where we say V is all binary strings of length n, and the set edge is the set of all the unordered pairs of VW such that, so we call that V and W are now strings. So V and W differ only at a single place. For instance, here we have 100, so 100 is connected to 110. You see that a 0 is changed into 1, and so it's 0 is changed, 100 is connected to 101, where the first 0 is changed into 1, and on this edge the first one is changed into 0. And therefore the degree of every vertex in an hypercube is exactly the number of bits in it, because you can change each one of them and you go to another vertex. And the structure of this graph is like an n-dimensional uh, cube. And so the reason it's called n-dimensional cube is that so if you take, well, the uh, Cartesian product of an integral with itself times n, and then it lies in an n-dimensional Euclidean space where the points were in that cube, n-dimensional cube, have integer coordinates, are the vertices of an hypercube. All right. So, but you don't need to know the higher dimensional things, and you just need to know this definition here. Another class of graphs are bipartite graphs. So let me give a definition. A graph G, let's again, G is the ordered pair of VE. It's called a bipartite graph. If V, the set of vertices, can be partitioned into two disjoint sets. So when they say partition, they always mean decomposing the set into disjoint subsets. So if we can write V into disjoint, if it can divide it into two disjoint subsets and write it as V equals V1 union V2, and such that for all edges E, we have one endpoint of V in one set and the other endpoint in the other set. That is, you can subdivide the vertex set into two parts where where all the edges go between these two parts and no edge goes in a part. Right, so you can divide all the vertices of the graph to two parts where your edges are between these two parts. So let's see, this is E1, this is E2, and this is E3, and you cannot have any edge that goes inside one part. And there is a terminology of a complete graph, a complete bipartite graph with parameters m and n, k and n, is where intuitively you take two sets, one m vertices, and you take another n vertices, and you connect all possible edges between them. So this is called the complete bipartite graph with parameters m and n, k and n. For instance, K1, 3 is the graph So you put one vertex at one side and three at the other, and you connect this one, all the three. And K2 is you take two sets of two vertices each, and you connect this one, and this one to this one. And so there is no edge between any of these vertices of any of that are inside any one part. Now it's possible to actually play a lot of games with a given graph. And one of these kinds of games that people try to play on a given graph is coloring it. And these colorings have very applications are very important also. And some we can color vertices of a graph or we can color edges of a graph. And coloring usually means you assign a color to the vertex. So let's have a graph. So for instance, this one. And by coloring the vertex, we just uh, it's very important how many colors we allow. For instance, if we allow only two colors, red and blue, so I can assign one color to each vertex. And this is called coloring the vertices of a graph. So it's a very intuitive notion that you color each vertex. Now let's see a very nice theorem about bipartite graphs. A simple graph is bipartite if and only if it is possible to assign one of two different colors, like red and blue, and this means coloring it by two colors, such that each vertex gets just a color and no two adjacent vertices are assigned the same color. So this is a very usual condition in coloring, that you want to color in a way that no two endpoints of a single edge, which are called adjacent, so no two adjacent vertices get a single color. For instance, here, this is a coloring which is valid by the definition of the theorem. And but if I had instead colored this one here red, then we have now three edges with the same color on both sides, both endpoints, and therefore it's not valid by the definition. And now the theorem says that a graph is bipartite if and only if you can color it with this property that each edge has two colors. So let's try to prove this. Note that for like any other if and only if statement, we have two directions. So first is the if direction, and that says that it's the usual direction. If a graph is bipartite, we can assign. So imagine therefore G, by assumption, G is bipartite. Then if G is bipartite, we have V to be V1 union V2 as before, with the property that no edge connects things in V1 into itself. And now it's very easy. Take V, color V in V1. So let's see, color vertices of V1 blue, and vertices of, so here is V1, V2 red. Then it is just the definition of bipartite graph that all of the edges go from V1 to V2, and therefore all of the edges have to have two different colors. Therefore, we have a valid coloring of the graph. Now let's go the other direction. Now let's have a valid coloring. Then define V1 to be the set of blue vertices and V2 to be set of red vertices. Then again, it is the definition of valid coloring that no edge it connects a blue vertex to a blue vertex or a red vertex to a red vertex, and therefore every edge has to go from V1 to V2. And therefore, these two union of these two is the whole set of vertices, and therefore we have correctly partitioned our graph into two pieces. Okay, so now if you have this vertex were blue, then this theorem says that this proof tells us that you take this 2 to be V1, for instance, and these 3 to be here V1 and V2, and now each edge goes between these two sets. Let's go into the notion of a subgraph. So intuitively, a subgraph is a graph which is part of a bigger graph. And so let's have two graphs, G with vertex set V and H set E, and H with vertex set W and H set F. Then we say that H is a subgraph of G if its vertex set is a subset of V and its edge set is a subset of E. And H is called a proper subgraph of G if they are not equal. So for instance, if G is this graph and H could be the graph which, so let's give names to these. Then H, you just remove some vertices and edges. So for instance, it can have some vertex here, some B and E2. So for instance, H then here is a subgraph of G because its vertex set is a subgraph. Sorry, is a subset, and its edge set is a subset because here it has just one edge, but that edge also exists between BC here also here. For instance, but note that if we had an edge here, it couldn't be, H is not then a subset of G because the edge between A and C does not exist in G. Another related notion, which is very important also, is called the induced subgraph. So induced subgraph is of a vertex set. Induced subgraph with over a subset W of V So again, so I'm assuming that G is the set D graph E, and the induced subgraph is the subgraph H with WF. So the vertex set is just the given set W with and F, sorry, all edges of G connecting vertices in W. Intuitively, in an induced subgraph, you just take a subset of vertices and you put in every edge of your original graph that connects vertices from this subset that you've taken. So let me give an example of it here. So let's take a set, for instance, S of I'm referring to this graph here again. So S, let's take S to be A BX, then the subgraph induced by S is of this graph G here. Okay, we just have A, B, and X, and now we see which edges of G connect these vertices. So, and we have only one edge that connects A and B, and that's called E1. And so there's no other edge that connects vertices of S with to themselves. And so therefore this graph here is the subgraph induced by S in G.